Okay, class, welcome back. What we're going to be talking about today is continuing with our finite depth box, but really focusing on what is going on with our wave function amplitude as it exists in this classically forbidden region here. And what that results in is a really interesting phenomenon called tunneling. So when we start talking about tunneling through a barrier, we first want to talk about what's going on in the classical world. So an energy barrier cannot be cleared without sufficient energy when we're talking about classical physics. So when we think about something that has a barrier of energy, we might think of like an activation energy, right? So an activation energy can't be cleared unless you have a certain amount of energy to get over that hump. In quantum, however, particles can penetrate classically forbidden areas. So whereas in the classical world, you can't go through a hill, you have to kind of go over the hill. In quantum, particles can actually go right through that hill under certain circumstances. So what's happening here is we have particles penetrating a classically forbidden barrier. And the reason we're able to do that is because we have a potential energy wall that is some amount of potential energy, not an infinite amount. So the wave function amplitude in that wall decays rapidly, right? So that's what we were talking about last time when we have this wave function decaying rapidly as it exists in the classically forbidden region. So the wave amplitude decays rapidly. However, if the barrier is thin, so for example, on the order of the particle's de Broglie wavelength, the particle can escape right through the barrier. This is the phenomenon called tunneling. So, to get a better understanding of how tunneling works, let's do what we normally do, which is first defining our potential energy. So, inside box 1, so we're going to be looking at box 1 over here, separated by a barrier from box 2. Inside box 1, we have a potential energy that's based on x that is equal to 0. And the reason for that is, of course, inside the box, we have all kinetic energy. Over here on the right side, inside box 2, we also have a potential energy based on x that's equal to 0. The reason being, inside the box, we have all kinetic energy. Now, inside the barrier, we have a potential energy that's equal to V naught, meaning that V naught is some amounts of potential energy. Since we have a finite depth box, we are no longer dealing with V infinity. This is not an infinite amount of potential energy, this is a finite amount of potential energy. That's the whole reason why this is possible. So, when we're looking at two boxes that are separated by a barrier of some amount of potential energy, let's take a look first at what's going on in box 1. Here we have a wave function. And this wave function is not 0 at the walls, just like we defined last time. If you were to skip back through and look at the trend of how our wave functions increase and correlate that with the number of nodes, you would be able to see or deduce that this wave function here would be wave function 7, where n is equal to 7. So we have 6 nodes, 6 points at which the wave function is 0, which correlates with wave function 7. So the reason why we're doing 7 is because, as a reminder, the greater n, so our greater n value, we increase our amplitude outside the box. So the greater the n, the more significant the amplitude is. The square of the wave function is the probability, so we have a greater probability of finding the particle outside the box. It's not a lot, but it's enough. And for us, outside the box, we're talking about inside the barrier. So the higher the value of n, the greater the probability that we will find a particle inside the barrier. So when that happens, what does it look like? Well, first we would see that it decays rapidly. So we have some amount of the wave function inside the barrier, but it decays really quickly. But we can now see that at the wall of box 2, that wave function is not 0. And if it's not 0, well, then it can go into box 2 and give us some other standing wave. Now, the amplitude of the wave function in box 2 is significantly smaller than the amplitude of the wave function in box 1. That's because it lost a lot of its energy traveling through this barrier. But once it exists inside box 2 with some amount of potential of kinetic energy, it will then form a standing wave inside box 2, which is enough for it to exist. So it lost a lot of energy, still has some kinetic energy, still forms a wave function in box 2. So this is bouncing back and forth as a standing wave, and every once in a while, some amount of the wave gets transferred over to box 2. So what we're going to look at next is quantifying this decay. So as we turn now to wave function decay, inside the box, we have our equation from last time. The second derivative with respect to x of the wave function is equal to negative 2 times the mass times the energy. Inside the box, remember this energy is all kinetic, divided by h bar squared times the wave function. Now, what we're going to do is redefine some of these terms. So we're going to say is that k squared, this is a k, is equal to that whole value here, negative 2m times the energy divided by h bar squared. So then if we substitute k squared in for that value, back into our Schrodinger equation, we have the second derivative with respect to the wave, with respect to x of the wave function is equal to k squared times the wave function with respect to x. So we have k squared. Now what we can do is solve for k. So we just take the square root of that whole value, and there we have it. K is now equal to the square root of negative 2 times m times the energy divided by h bar squared. So after all that work, what is k useful for? For us, not a lot. But what we're going to be really interested in is our next set here, outside the box. And remember, outside the box for us is actually inside the barrier. So this is going to be what's happening right here, inside the barrier. So using our equations from last time, we have the second derivative with respect to x of the wave function is equal to positive 2 times m times the difference in potential energy and that kinetic energy, or total energy, divided by h bar squared times the wave function. Now, instead of k is the variable that's used inside the box. We're going to use this, which is actually kappa. So this is not a k, this is the Greek symbol kappa. So the way that I'm going to be drawing that is a kind of small, bold, stout-looking k. So just make sure that you change your own handwriting to indicate that it's not the same as a k. So let kappa squared equal this whole value. 2 times mass times potential energy minus the total energy divided by h bar squared times the wave function. And so we can then solve for our second derivative with respect to x of the wave function, and that's going to be equal to kappa squared times the wave function. And then we can isolate the kappa variable as being equal to root 2m times the difference in energy divided by h bar squared. So that is our value for kappa. So k, not totally useful. Kappa, very useful, because kappa can be used in two equations. So first, we have our equation for decay. And our equation for decay of our wave function is equal to a coefficient a times e raised to the negative kappa times x. So once again, that is our kappa. That is not k. So our decay is the wave function a e raised to the negative kappa x. Our decay length, so the actual length of that decay inside the barrier, is equal to 1 over kappa. Nice and simple. So let's take a look at our trend in decay length. So if 1 over kappa is equal to our decay length, that is going to be equal to the square root of the denominator and numerator flipped. So it's going to be the square root of h bar squared divided by 2m times the potential energy minus the total energy. So if we just add some numbers in, and we have our potential energy is equal to 1, and we set our total energy to be equal to 0.9, we can plug them in and get a really hand-wavy estimate for what 1 over kappa would be. And this number that we're calculating is absolutely meaningless, but it'll allow us to see a trend. So 1 over kappa is going to be equal to square root of, we'll just say 1 over 1 minus 0.9. And that would be 1 over 0.1, and so the square root of that's going to be 3.16. So if we keep our potential energy the same and take our total energy and decrease it from 0.9 to 0.3, then we'll have 1 over kappa ultimately equaling 1.20. So of course we just held the mass of an electron constant, h bar is a bunch of constants, so this just allows us to isolate the trend. And I purposefully made sure that total energy was less than potential energy, and that's because in our barrier, our potential energy is greater than our energy. It's not so high that it's equal to infinity, but it is greater than the total amount of energy. Remember, if we were inside the box, this would be flipped because we would have all kinetic energy. But inside the barrier, we predominantly have potential energy. So, as a result of this trend, as energy increases and approaches our potential energy, the decay length of the wave function amplitude increases. So, our wave function is in the barrier and it's decaying rapidly. But if our energy is approaching potential energy, it takes longer for it to decay, and it actually extends out a longer physical distance. So, as our energy increases and approaches the potential energy, the physical distance of decay length increases. So more tunneling is possible for higher energy particles. And for us, that means that as our n value increases of psi sub n, so as our n value for our wave function increases, tunneling becomes more possible. So, one of the applications of tunneling is for an instrument called a scanning tunneling microscope, which is often abbreviated simply as an STM. So before we start talking about a scanning tunneling microscope, we have to sort of redefine how we're going to be looking at our wave functions. So consider two conductive materials. If we have conductive material 1 and conductive material 2 and they're separated by a barrier. Each material is made of stuff, and that stuff has many, many energy levels with many, many electrons. So we've been looking at first would be something like this, where we have one material which is made of a box that contains a whole bunch of wave functions, and our second material is a bunch of energy levels which contains a bunch of wave functions. So we have here some electrons. If each one of these energy levels had 2, we would have 12 electrons in each one of these boxes. So we have some amount of electrons, and we have clearly defined energy levels. Now, if we were to start talking about more of a material, we would have many, 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 many electrons. And we would have a large group of energy levels. So we would have so many overlapping energy levels that they wouldn't be able to be distinguished from one another. So in inorganic chemistry, we call this a band of electrons because we're not really looking at clearly defined energy levels anymore. So that's how we're going to be looking at things for the next topic. So in a scanning tunneling microscope, the barrier between the two conductive materials is a vacuum. So that's our barrier. And electrons are induced to tunnel from material 1 into material 2. Material 1 is going to take the form of a tip. So this is going to be our material 1. And it has a single atom for the size of its tip, which is pretty amazing. In material 2, that is going to be our surface. So what we're going to do is see how we can induce tunneling to occur from one material, our tip, to material 2, our surface. So in a scanning tunneling microscope, our decay length, 1 over kappa, is occurring through a vacuum, and our vacuum is our barrier. Now this has a physical distance of about 0.1 to 0.5 nanometers. So for reference, a carbon-carbon single bond for an sp3 hybridized carbon is about 1.54 picometers, which is equal to about 0.154 nanometers. So we're talking about a barrier that's a vacuum that's about as long as a carbon-carbon bond, which is really, really close. So a lot of engineering goes into, first, being able to get the tip and the surface in this system to be that close to one another, without touching, which is pretty amazing. So if the tip and the surface are closer than 1 nanometer, tunneling from the tip to the surface can occur. So I said that the tip of the surface is a single atom, and that's achieved by essentially electrochemically etching the wire. So it's a chemical process or electrochemical process that's used to really just polish down the tip of a wire. And no matter how polished you get this thing, eventually there's always going to be one atom at the tip that protrudes slightly more than the rest. So there will be other atoms that are nearby, but the next closest atom ends up being an irrelevant distance because we're dealing with such a small area. And once we have tunneling, so once we've achieved getting the tip and the surface to be between 0.1 and 0.5 nanometers, we can induce tunneling to occur, and that tunneling increases by an order of magnitude every 0.1 nanometers. So if you have a next atom that's about 2 or 0.2 nanometers away or something, then it's really not that close, and so our tunneling is going to be significantly increased. So, how do we get tunneling to begin? Well, what we need to do is use a voltage to initiate tunneling. So here we have is a diagram that's showing generally the amount of energy of the electrons in the tip and generally the amount of energy of the electrons in the surface. So you can think of this as increasing in energy on the left. Now, the tip is lower in energy than the surface, and they're isolated from one another. So to begin with, we have the tip coming in, and we have the surface. So they're not connected to one another, they're isolated, and the tip electrons are at a lower energy. So all of these wave functions that are overlapping, they are at a lower energy, and all the wave functions that are overlapping in the surface are at a much higher energy. Step 2 is seen in figure B, where we actually connect the tip and the surface. So the tip is getting really close to the surface, but in this distance we have a vacuum, but it is connected by a wire. And once they're connected, the energy between these equilibrate. We have electrons being transferred from one another, from the direction of the surface to the tip. So even though that there's a vacuum from here to here, we have electrons get immediately transferred over, and then the energy of the tip and the energy of the surface become equal. So you can see that those are now at equal heights. Now, the third and final step is the crucial one. So here, what we have is a voltage being applied. So once you apply a voltage, you can increase the energy of the electrons in the tip relative to that of the surface. And that combined with having the tip being within 0.1 to 0.5 nanometers of the surface, you can get the standing waves of the electrons hitting the walls, hitting the barrier at a certain amplitude, decaying rapidly through our barrier, but hitting the next box and then forming another standing wave. So we have our wave function in the tip. The highest energy there decays through the barrier, which is about 0.1 to 0.5 nanometers, goes into box 2, which is our surface, and there it continues existing as a standing wave. And we have actually transferred an electron through space, through a vacuum, from one material to the other, from the tip to the surface. So after our voltage is applied, our tip is higher in energy, and that is what allows this decay to happen through space. So the instrument does a fantastic job of measuring the current between the tip and the surface. So if the tip is directly over a surface atom, the amplitude of the wave function is large and the tunneling current is high. If the tip is actually between surface atoms, the amplitude of the wave function is small and the tunneling current is low. So here, what we have is a diagram showing the tip and the surface. And so the tip is sort of moving laterally in a plane in space. And anytime it is directly over a surface atom, you get tunneling through space, and there is a change in the current, and the instrument measures it. If that single atom is of the tip that's protruding the most is between atoms, then there's less current because there's less tunneling, and it can tell the difference between that. And if you plot the amount of current flow in an image, you get incredible resolution. So this picture here is an image of silicon atoms. So these are single atoms of silicon, and you can see the arrangement for the very first time as this honeycomb type pattern. And that's all made possible from single electrons of a material being induced to tunnel through space into a surface, and then measuring the change in current flow. And so that's it for now.